Hello everyone, thank you for joining this XFlow webinar. My name is Zaki Abiza, I'm from the XFlow business development team. In this webinar, my colleague Rudy Brionneau will introduce you XFlow Acoustics capabilities, and he will also show you the results of the LAGOON landing gear benchmark. You can send, during this webinar, you can send us all your questions. You can use the questions box at the right. We will try to answer all these questions during the webinar, and some of them we will keep some of them for the questions and answers session at the end of the webinar. Before we start the webinar, I would like to to check the audience of the profile of the audience today. So if you can answer these polls for us, just to check the profile of the audience. I will let the question during a few seconds so that everyone gets get time to answer. Yeah, 5 seconds, and we will close the poll. Okay, so thank you for voting. So we have a quite distributed result of for this poll. We have a quarter of the audience have already used XFlow on Aeroacoustics, and the rest didn't use it. Thank you for answering this poll, and thank you for joining this webinar again. I will let you now with my colleague Rudy Brionneau, who will introduce the webinar for you and introduce himself and present the webinar. Thank you very much.
Thank you, Zaki. Thank you very much. Hello, everybody. Thank you for joining this webinar again. So my name is Rudy Brionneau. I'm the lead XFlow Application Engineer. And today I'd like to share my experience on the aeroacoustics analysis with XFlow, show how Lattice-Boltzmann is really a good method for this kind of problems, and apply it on a very good benchmark for these aeroacoustics applications, which is the LAGOON landing gear. Okay, so I'll explain that during this presentation. So today the outline will be first a short introduction to XFlow, because eventually some of you don't know our product yet, so I can explain a bit our differences with other CFD software, Lattice-Boltzmann method, and how it is applied to aeroacoustics application as well. Then we'll go through the landing gear, LAGOON landing gear test case, where I explain a bit the setup of the simulation, and also what kind of problem we're solving here, the type of geometry, and so on. And then we'll review the results obtained with XFlow about 2D velocity planes, pressure coefficient, velocity profile, and unsteady wall pressure for acoustics. And finally, I'll do a very quick live demo on XFlow to show the possibilities that you have to do acoustics post-processing with the software. So let's go for it. Again, as Zaki said, you can send us your questions to the question box on the right panel. So do not hesitate to send the questions. Eventually, we'll answer them at the end of the webinar. Okay. Now let's go through the first slides. So we'll start with the XFlow introduction. So for that, I'd like to explain what you may be used of, which is a traditional mesh-based CFD approach. That means Navier-Stokes codes mostly. And here you can see that what the abilities that you need to combine to actually perform a simulation with Navier-Stokes solver. So usually you need to have a very good combination between the mesh, the turbulence modeling, and also the numerical scheme. So first the mesh, because you all know that probably meshing the free domain is really painful as application engineers. I know myself it is very time consuming. Also the solution quality will be very dependent on your mesh quality as well. So it's usually a lot of time consumed and also a strong dependency of your solution on this mesh. Also it's a main constraint for moving boundaries as well. On the other side, we've got the turbulence modeling, which is normally limited to Rance and Reynolds average Navier-Stokes models, such as Paratamaras, K epsilon, K omega, and so on. These are used because LES is normally too expensive for these methods, and DNS as well. So Rance is a semi-empirical models, and so that's usually not very, very good when you want to have a very high fidelity models for turbulence description, as this is the case, for example, for the aeroacoustics application, which are very much dependent on how good you resolve your turbulence as well. And lastly, we've got the numerical scheme, which, as you know, Navier-Stokes is not a trivial equations to discretize. So usually we've got difficulties with a nonlinear advection term. Your code usually needs also to add some artificial viscosity so that it converges without any numerical issues, and this type of artificial viscosity also damps the physics, especially for unsteady flows, especially for acoustics, where on the contrary you try not to damp things, but you need a very high scheme orders in order to maintain all the pressure and acoustic fluctuations in your flow. So to get rid of all these three problems we've got with the mesh-based solutions, we tend to overcome them with the Lattice-Boltzmann methods using a different discretization scheme based on particle-based approach, and that means we've got no manual meshing. Also it can handle any type of complex geometry. On the other side, we've got the turbulence, which is modeled with an LES and wall function, and finally the numerical scheme, which is much simpler. So now I'll get into the details of each of the three, let's say, solutions provided by Lattice-Boltzmann. So first, on the discretization scheme, which is based on lattice, as the name of Lattice-Boltzmann stands. And the lattice is just this distribution of points, so it's basically the mesh you use in Lattice-Boltzmann to discretize your free domain. And these points are connected together, okay, that's like a network of points, and that's how you stream or collide the particles, basically. And so this discretization scheme is very easy, allows to generate with an octree structure very efficiently near the geometries, for example, on the far field or even on dynamic criteria such as wake refinement, let's say a spacing that you input yourself. So for example, this wing profile here we can see has been discretized with 5mm resolution near the wing, and then we just have to specify a far field resolution of 1.28 meters, and automatically XFlow generates the different lattice levels automatically. Okay, you can also refine dynamically the wake, for example, with 1 centimeter wake refinement, and that's the way it works. So you can see we've got support for multi-resolution. You can discretize geometries with no troubles. It's usually very tolerant to the geometries as well. On the other side, the turbulence, which is in this case LES with a law of the wall, okay? So that's what I was explaining before, but most codes use Rance because it's very expensive. You know that turbulence is basically the Kolmogorov cascades, where you've got a large eddy that's separated into smaller eddies and so on, dissipating energies isotropically. And so what you need for Rance is modeling all the scales. So basically you filter all fluctuations due to turbulence, and you just model all of them at any eddy size. On the other opposite, you've got the DNS, where you resolve absolutely all scales, even the Kolmogorov scales, which are very small and can be very expensive, and it's usually not practical at industrial level. On the other side, using LES, you just resolve the biggest eddies, and then past a certain size, you just apply a model so that you model the smallest size that you can't capture. Okay, that's what we do with XFlow. We just, let's say, resolve up to the lattice size, and you've seen previously we can specify the lattice size, and you've got this relation of 2 between the lattice levels. And then what you do is just model every eddy that would be smaller than the lattice size. We use a wall adapting local eddy model in this case, which is known to perform quite well. Okay, and in addition to that, we use a generalized law of the wall that allows you to, let's say, model the boundary layer, of course, because being Cartesian, the mesh and the lattice structure, it would be extremely expensive to refine all the boundary layer near the walls. So instead we use a wall function which combines perfectly with our LES approach and allows you to get this LES at a very reasonable cost. So I was saying that LES is very expensive for the Navier-Stokes codes, and I'll explain and demonstrate then in this actually presentation in the LAGOON test case that it's true for an LES unsteady simulation. Navier-Stokes can be much longer and slower than a Lattice-Boltzmann code, and that's what I explain later. Okay. In the meantime, 3 important things that makes the LES very well suited for Lattice-Boltzmann is that we use an isotropic mesh, which is a lattice, which is perfect for the isotropy of the turbulence. Also, Lattice-Boltzmann is unsteady, so it's perfectly suited for LES. And finally, it's much faster in computation, as I will explain later. Now we can speak about the numerical scheme, which is in reality much simpler than the Navier-Stokes equation to resolve. So that means we've got much less struggle in terms of numerical scheme to resolve that equation. So the equation we resolve in Lattice-Boltzmann is obviously the Boltzmann transport equation, which is the one you can see here. On the left side you've got streaming term, and then on the right side you've got a collision term. So that term is actually streaming the function f you can see here, and the function f is what we call the particle distribution function, okay, PDF. To make it shorter, we usually speak about PDFs. Okay, and these PDFs are what we use to model, let's say, the molecular agitation. That's a statistical description of your particles, and we use them to recover macroscopic variables. So basically, just integrating and computing the statistical moments, we can compute density, linear momentum of the particle of fluid through these functions. On the other side, the collision operator is usually the term that is the most delicate, and in XFlow we use our very own approach of collision operator based in central moment space, and that implies a higher space accuracy, lower dissipation, and a stable scheme. So basically that allows us to get more accuracy and less numerical diffusion in that case, which is very important, for example, in this case in the Aeroacoustics, which normally codes struggle in really getting to high orders methods. So just to explain the differences between approaches to acoustics, we've got several ways of approaching acoustics in CFD. Imagine you've got a steady state CFD. So you get a mean aerodynamic field, okay? So you model your turbulence with, for example, a Rounds model. And then since you don't have any fluctuation, you have to model the source of acoustics, because normally the source comes from the fluctuations of pressure in your fluid of domain. And then you've got also to propagate this source of acoustics, and then you'll get your acoustic pressure field. On the other side, you can use an unsteady CFD, for example, for incompressible flows, which makes equations simpler. However, if you do that, you're going to get the fluctuations, but you're not going to be able to propagate these waves because of incompressibility. And that's where it comes when you want to do direct noise computation. That means when you want to actually compute the fluctuations of pressure that are related to acoustic modes, then you need to use a direct noise computation approach, which is usually unsteady compressible flows, and that requires high order schemes so that waves don't dissipate as they are being propagated. All right? So this is where we stand with XFlow, and we actually get rid of all those models here, turbulent, acoustic, source, and propagation. And we just get our acoustic field directly through the pressure fields. So we just have to measure waves propagating and we'll get acoustics. How we do that? Well, very simply, for example, for a gas, you know that speed of sound relates actually your fluid properties to the speed of sound, and this is the ideal gas law here. So you've got adiabatic index, the temperature involved, and so on. And so through this equation, you know for this type of gas at these conditions, what is your speed of sound that you should get. So let's say, for example, air at regular temperature should be about 340 meters seconds. And on the other side, when you have your lattice scheme defined with a certain lattice size, which is dx in this case, you know that the next neighbors will be spaced by dx, and you know that you've got a dt value here that will stream the PDFs that you remember earlier. We've got streaming of the PDFs along the lattice, so you know that the numerical speed of sound, which is the pressure waves traveled in the simulation at the following speed of sound here, which is a relation of dx over dt. You've got, let's say, square root of 3 here for lattice isotropy, but basically it's just dx over dt. And so that adjusts the speed at which you propagate your information. So this is why you've got actually a relation that you must fulfill to get the speed of sound you need, which is this CS here that you want, for example, through the ideal gas law or any arbitrary speed of sound, must be equal to your numerical speed of sound, which in this case with the ideal gas law gives us something like this, well, with any speed of sound actually. So we get, let's say, a condition on the time step for a given resolution. So if you fix your resolution of lattice, if you want a certain speed of sound, you get a unique time step to fulfill this speed of sound. And so you see, for example, this is what you get here, is if you've got a small perturbation in the center of your empty domain, for example, initially we just throw a pulse, and then this pulse will just propagate, as you can see in this simulation here. So this propagation will be streamed by the streaming of the PDFs, and this will be relaxed with a collision operator to equilibrium state. So we already see all fluctuations of fluid due to compressibility of the fluid in Lattice-Boltzmann, which is why also it's very good. And because of that, because the streaming is exact in Lattice-Boltzmann, we get also a very low dissipative scheme for this direct noise computation approach. So now we are done with that. I'd like to speak about the LAGOON landing gear setup and show you a bit what we've done in this case. So this is the following. The LAGOON landing gear is this geometry you can see here. So just to give you a bit more of details, this benchmark is part of the BANC workshops. The BANC workshop is let's say, a gathering of different workshops proposed by the most important aeronautics companies and institutions in the world, such as Airbus, NASA, DLR, JAXA, and so on aero as well. And so all these institutions propose to share with us and share with anyone interested in validating their CFD code and sharing the data so that we can build some know-how and best practice on CFD for these applications. Well, run these cases and you get access to a large database of experimental measurements, which is extremely good and reliable. So one of the categories of this BANC workshop is actually the LAGOON, category 5. This LAGOON is just a simplified landing gear geometry that you can see. It's just only 2 wheels, a leg, a strut, and that's pretty much it. So very simple, but still, despite of the apparent simplicity of the geometry, it's not that easy, and acoustics is very complex in this region, and codes really struggle in getting that right. So for this case, it's been tested, I think, in 2 wind tunnels, which are the F2 and the CIPRA 19, which are respectively for aerodynamics and aeroacoustics. And so a lot of data have been measured on that LAGOON landing gear, which are probes of pressure, let's say pressure coefficients, velocities, profile with PIV, and so on. And of course, pressure fluctuations for acoustics. So the conditions are here described and summarized with fluid being air, speed of sound being the regular 340 meters second speed of sound, and we've got boundary conditions of approximately 78 or 79 meters second. Okay, so what we do is we impose that inlet boundary condition on this size here, okay, and on the outlet we apply a gauge pressure outlet of 0 relative Pascal. On the sides and top, bottom we apply periodicity conditions. This domain size has been chosen so that we don't have any border effects or large enough so that there is no effect, okay, on the simulation. And then we had to go through a refinement strategy, which in this case has been, well, refining by 0.5 millimeter near the geometry and employing then several boxes of refinement, user-defined boxes of refinement that you can create to refine certain regions of fluid. So in this case, that box is set as 2 millimeter resolution. And then we've built some larger boxes, you know, that are larger than the previous one. So you've got 2 in red. Then out of the red box you've got 4, and then 4 millimeter as well on that green box, and then you've got 8 millimeter here as well, and so on. So with that we actually have a refinement that is progressively, let's say, unrefining, right? So we've got a finer resolution near the geometry so that we can capture the smallest fluctuation of the smallest gradients of fluid, and then we just progressively unrefined so that the computation cost also becomes accessible, and so that we don't have any too strong, let's say, a transition of lattice in between the geometry and the far field, so that you can capture the wake conveniently. So this leads to a total of about 59 million of elements of lattice nodes, and well, that's quite a lot, and that's quite well, important simulation. So we run about 0.34 seconds of physical time. After that time, usually the spectra were all converged, so that's why we were actually okay with using that much simulation time. And the minimum time step, because you've got different time step at different lattice levels, but the smallest one, which is near the wheel and geometries, would be about 8⁻⁷ seconds, which means we've got quite high sampling frequency as well, since we've got 1180 kilohertz of sampling frequency, which is important for acoustics as well. You need to extract information at a good sampling frequency in order to have, let's say, a good quality signal processing. So total CPU time was about 32,000 CPU hours. You'll see after that it was actually quite lower or much lower than most of the Navier-Stokes codes, for example. So here you've got a good view of the lattice structure near the walls and a bit further. So you see, we see very clearly the red box of refinement here, which is 2 millimeter, and we've got 0.5 millimeter near the landing gear. Okay, and you've got a transition level of 1 millimeter, then 2 millimeters, and then the other levels. Also, the data has been averaged for some data such as, for example, comparing flow structure, velocity profiles, and these kind of things. Since you get the instantaneous data, you need to do and proceed in averaging your data. So we've got that possibility and that capability in XFlow to average data to get, let's say, the mean value of your flow field. So what we do is we average data from 0.05 seconds, since we got a small and short transient period that we consider was over after that time. And so we can use all that range of data here from 0.05 to 0.34 seconds to use as data averaging and signal processing. So here is a small summary and comparison with most of the codes that have been running this workshop. You've got on the left side some, well, let's say that's an average of the output data from the Navier-Stokes code running this this benchmark. You can see, you can check on the reference below, actually this, this reference to get the exact numbers if you'd like. The table is available in the paper. And XFlow on the right side. So you see, for example, for most of Navier-Stokes code, they were all using actually not even LES, but DES, okay, or zonal DES as well. DS is quite actually quite less expensive, quite cheaper in terms of computation than LES. So we are speaking about simulations not even involving LES yet. So in our case, we are using LES with whale turbulence models, the wall adapting local eddy model that I mentioned before. And on the other case, we're mostly using Sparta, Maras, OK, Omega SST for the subgrid models. So simulation size, you see, also are about, well, larger for XFlow, unless I understand you can't really compare directly mesh size in Navier-Stokes than in XFlow. Just that was about 30, 40, 50 million elements, so we are speaking about large mesh sizes. And what is important really here is the last line where you can compare the computational costs of different codes, Navier-Stokes codes compared to XFlow, which was only 32,000 our CPU, and whereas the other codes were mostly using about 200,000 CPU hours. So that's about a factor of 10 times longer for the same, not even the same, since it's a DS simulation results. So you can see Lattice-Boltzmann is very quick. We usually speak about an order of magnitude faster than Navier-Stokes code for unsteady LES simulations, of course. So if you compare a Navier-Stokes simulation running unsteady and running with LES turbulence modeling, it's very likely XFlow will go at least 5-10 times faster. So that's what we've done here. On the left you can see all the sensors, the taps and the coolites. So the coolites are for measuring some acoustics values, so spectra of pressure, and then here you've got some other pressure taps where we measured actually the pressure coefficients. So our acoustic results now, we'll start with 2D velocity planes. So this is a very short animation of the simulation. You can see here, this is a velocity field. So we can see we've got a cutting plane of velocity showing the wake induced by the leg downstream, and also we've got the projection of velocity over the geometry, and you can see a very steady velocity field on the front side, but on the downstream side a lot of fluctuations, especially inside the geometry you can see here. These are due to the turbulence generated past the front wheel, and this turbulence will induce a lot of fluctuations and also therefore a lot of noise, which is where we study this aeroacoustics. So in this case we've got the comparison between XFlow and experimental PIVs. Okay, so that's basically measurements in the wind tunnels where they represent the velocity fields. Okay, and so we just compare with XFlow. I just highlighted the areas of comparison, which is basically this box here is represented in this box here, so you can get a reference value of how long should be the wake and so on. And we can see it's pretty well matched, and so we've got approximately the same size of wake, the same shape of V shape of wake as well, larger separation between past the wheel, sorry. And then on the, well, that's the U velocity, so that's the streamwise velocity here on the left. Then you've got the transversional velocity, so on that direction from left to right, and then on the right W will be the from top to bottom velocity components. So you can see here also we've got the same patterns of flow field with the red area and blue area here. And here at the same time we've got some lower values here and higher value here. So that was for plane, sorry, at Z equals 0 millimeter. That means just in the middle section of the wheel seen from the top, right? Now if we change the Z direction and go to a plane, a cutting plane that is slightly above that, so we are just on top of the wheels, We've got other planes as well, so we can see here again same comparison. So we've got the same large wake size here with some separation right there and there, with higher velocities of these areas here. Then we've got also the same round high values here and low values there than here, and we've got the same type of wake as well here. And finally, small bubble here of blue, and then again it's approximately the same size of wake as well. And now the same thing, but with a plane that is at z equal minus 104 millimeters. It means slightly below, so we're at the lower height on the wheel. And well, similar again patterns. So we've got high velocities in the middle, this green area like this here, with bluish regions here. Here as well, it seems to have the same patterns of blue, red. And finally again, we've got that greenish area, and here's a reddish area as well. So we don't have scales here, but actually velocity values and velocity scales were taken at the same ranges, of course. Okay, so pressure coefficients now. Let's look at the different pressure tabs we had in the flow field. So you can see just before I comment the results, we've got here on the right side a let's say a graph showing approximately how the wheel is depicted. So you've got the flow coming from left to right. You've got the wheel that is this one that we see from the side view, and you can see that you've got a lot of different tabs located in front of the wheel where the flow comes, okay? And on the other side, you've got different cuts view where the flow also comes from the left to the right. And so in that case, you've got, let's say, on that height and in the front, different sections of the wheel, also 3 tabs, and then again, some other tabs on the locations here. So looking at, for example, 1 stands for the station here, 3 stands for the station that you can see here, and 2 stands for all the probes along the wheel circularly. So let's say the wheel's front region, the left wheel circular region, and the left wheel transverse region. So here we can see very well that well, the pressure coefficients is quite well matched by XFlow in comparison with the F2 data, which is where the wind tunnel where the tests have been conducted. And so you've got a good match of XFlow here and there, so symmetrically, of course, for the region 1. And then we've got also the region 2 here, that is also very well matched. So we've got obviously this CP equal to 1 around the stagnation point, and CP that goes lower and lower until negative values as you increase the angle. Okay, so that's the azimuthal angle you can see here. So here's let's say the trend has been correctly captured. We see 1 point is off, and it's probably a measurement problem, it's a measurement issue that was also pointed out by the committee. So the left wheel transverse also is pretty well and pretty accurate. We've got also 2 points that we suspect to be measurement issues, since they don't follow the same trend as the other points, but we see XFlow is very close and very nicely following that curve here that we've got here. So in the end, we're pretty happy with these results. Then we've got other locations, but not on the wheel now, on the strut, well, on the axle more exactly, sorry. And then you've got 1 point here that is station 1, and station 1 is located at the stagnation point where the flow comes from. So the flow comes from the left to the right, and you've got this point here that is used for measuring, and also 4 points that are located at different angles, so stagnation points on the separation area and at 90 degrees each. So you can see the stagnation point is well captured. Maybe the point here at minus 90 degrees is slightly underestimated here. That means maybe prediction of separation was too strong here, but on the other side it was correct, and then also on the separated area next to here. Now we've got also good match about 0.8 of pressure coefficients at zone 1 as well, which was good and close to the experimental data. Now, two other regions on the leg, so in the front with a distribution of points like this, and also circularly around the leg. So you can see on the first area, which is let's say linearly distributed vertically, you've got also a good match despite of a slight underestimation there, here, and then here as well. This point is slightly off, that we also expect not following the right trend, which could be due to measurement issues. And then on the other side, we think the following trend is pretty good as well. Here we've got again slightly lower estimation of separation maybe. So that's for the pressure coefficients. Now we also have the velocity profiles. So here also a lot of data available, so we won't show all the lines, otherwise you'll get slipping very soon, but just let's select a few lines here for this case where you've got all these lines have been measured in the wind tunnel, but we'll just pick up a few ones so that you can have a representative idea of how close the velocity profiles are captured. So you see on the left side we've got the U component of velocities, and on the right side the W component of velocities. So we've got U, which is in the flow direction, so from right to left here, and on the other side W, which is here in this case the vertical component of the flow. Okay, so we've got on that line that you can see here, which was line 4, on the top the average components of these velocities, and on the right root mean square values also. That means mean flow field and let's say fluctuations around this mean flow field. So on the top we can see the average values are well matched for this U component, slightly worse, but still okay in terms of velocity values here. We don't get that much of decrease here, but in general the trend then goes up again as expected. And then the fluctuations also are about the right amount here. We speak about 15 meters seconds of root mean square value of velocity, so that means fluctuations are pretty okay. Bit more deviation again, like in this area again, and here's the pressure fluctuations again are also good in that line. For the line 8, which is this one, slightly below that, so we're below the wheel alignments. Then here we've got again good trend, maybe slightly underestimated again, but good trend for the mean values, and then pretty good in W components. The URMS also is pretty close. We've got about 50 meters second again. That's pretty close to the measurements as well, and here as well. Line 7 now is a transverse line, so that's the red line you can see here. And that line is interesting because it crosses through different wakes, wakes of the wheel, left wheel, the right wheel, and slightly the strut as well. So it's interesting to see this profile. So we can see here the U component is very well matched, so we see really this high velocity out on the ends of the line, which is basically almost the free stream velocity. And then you've got this decrease, slightly stagnation here, which is due to the shear layer of the turbulence. And then you've got decrease again, which is basically when you get inside the separated area. And then again, increase of velocity when you're past the wheel, basically. And then you get, let's say, slower values due to the in-between cavity region and the leg as well. And again, drop against separation, stagnation area here, and then, oops, sorry, yes, just skip the slide. So then again, this velocity recovery. The same for the W component, very well matched. We've got correct profiles of velocity, and on the end we also have the correct fluctuations of velocity as well at the right level. Let's say we got the right trend with the peaks here, the flat area, the peak, and the zero value again. So obviously when you're on the ends there are not much fluctuations because you're in a free stream velocity, but then as soon as you get inside this shear layer and turbulent area, you've got fluctuations that are, well, very much important for the turbulent region, right? So that's about the right URMS values as well. And here as well, that's the same line, transverse line, but on the top now. So it's not anymore on the bottom, but on the top. And here you can see again that correct shape of let's say free stream velocity, shear layer, separated region. Recovery again, here we've got a higher value because we're on top, so we don't have the lag influence, and so we recover much more velocity in the flow, and about the same actually as free stream velocity, of course, and then again the same thing symmetrically. So the same with W, which is accurate, and the fluctuations as well are well estimated with the right magnitudes and the right trend as well. So I think we're close to the end of the results. Now the latest and most important one, because the first ones you've seen, of course, are more related to aerodynamics, I would say. But of course, aeroacoustics is a complex field. You need really to get the right aerodynamics in order to get the right acoustics. It's let's say all the art of combining, let's say, the impact of aerodynamics on the acoustic field, and that's what is very complicated to get. So basically you need to get the right acoustic fields to get the right solution in terms of acoustics as well. So we measured at different coolite stations the fluctuation of pressures. You can see here it's a video showing the pressure field on the geometry, so you can see the pressure coolite that was used for measuring the pressure fluctuation. Unsteady wall pressure are used, and you can see you've got a strong fluctuation in the separated region here. That gives your acoustic fields and the spectrum you want to look at. This region where separation occurs, you've got, of course, some regions where you can see some eddies and recirculations. So here, for example, we start with different coolites. So you can see here we've got, as a previous pressure taps for the pressure coefficient, we've got different, let's say, stations where we're measuring fluctuations of pressure. And here we're trying to not look at the mean pressure value, but now to look at their fluctuations. So to do that, what we do is we measure the pressure, let's say, history as a function of time, and then we try to process a signal and try to transform it in frequency space with Fourier transform. So in this case, we turned our signal, pressure signal, into frequency space to get, well, that's PSD in decibels, and compare with experimental data. So we're looking at a quite wide range. Note that the highest range goes to 20,000 hertz. That's quite a lot. And so what you can see here for coolites K3 and K5, which are basically those here and there, the flow comes from the left to the right. So these regions here are basically where the flow develops and then later starts separating. So we see that we've got a very good match of the spectra for these two probes. On the low frequency side here, it's perfectly matched. You've got also that small peaks here and there, and then you've got some more deviation here, which is mostly due because, well, we've been told in this workshop that they use a zigzag, I think, strip band, which allows also separation at higher, let's say, at lower angles here, and so very quickly separates the flow on a small layer here and generates more, let's say, fluctuations at higher frequencies here. So our spectra basically decays because we're in a region where no separations occur yet, because we don't have any strips for the turbulence here, and so that's why we've got these differences. So that's what we can explain. But basically it's extremely good on all that parts here. And also a lot of codes didn't manage very well to capture even these bits and very quickly drop then as the maybe also their scheme becomes more and more diffusive at high frequencies. When you damp, of course, the highest frequency are harder to capture because they require less diffusive or higher order scheme in general. So now if you look actually at the separated area, as I was explaining, now we're good because the spectra changes, and so we've got this shape of spectra that is matching very well here in that case, from the higher frequencies to the lower frequencies. That's pretty good. So we've got a very good alignment here on K7 and K9, which are this probe here and that probe here, because probably separation occurs around K6 or somewhere here. Now if we look at other probes, which are K14 and K15, that's interesting. That's the in-between cavity between the two wheels. So imagine here K13, 14, and 15 are in the inner side of the two wheels. And that's where you get, some resonance, let's say, phenomenon occurring. So that's why you can see these peaks here occurring as well that are very well captured by XFlow, these two peaks with the right frequency and the right magnitude. And again, at low frequency are very well matched. And then I think the result is good quality up to probably 2, 3, 4, 5, 6 or 5,000 or 6,000 hertz probably, which is very good. So you can see actually this is a video of the static pressure fields at very high frequencies, so that we can see a bit more what's happening. So you can see here you've got the probe 15 and here's the probe 14. So you see you're just in between the cavity, in between the wheels, and that makes an interesting phenomenon occurring, which is you've got this resonance. So you can see we've got a recirculation area here that goes around, and same on the other side. And you can see they slightly blink at some frequencies, and they are responsible for these two peaks of resonance here. So because you've got an in-between cavity effect. So now looking at other probes, we've got 18 and 20, which are located on the downstream side. And one is on the inner side and one on the outer side. Again, we've got some good match here, especially for K20, which is pretty good, even though on higher frequencies it drops a bit faster. And K18 is also pretty good here, slightly overestimated here and underestimated here, but overall it's a good match. And K24, 27, for example, on the strut here on the middle, on the leg, sorry, and then you can see that again, the level of accuracy is pretty good. We've got a spectra that is very close to the experimental data. And I think it's important to mention that most of the codes, and especially the Navier-Stokes codes, I mean, they can have some very quick cutoff frequency when the mesh is not fine enough, when you start being too diffusive, you don't capture the high frequencies necessarily very well. So in that case, a lot of codes had some big cutoff frequency like very early, too early, so actually you can probably compare with the reference I left previously, but XFlow results were among the best we could see during this workshop, showing that Lattice-Boltzmann is a very good match for this kind of problem. So this actually leads me to the reference here that you can check. First, workshop data measurements, LAGOON experimental database for the validation of CFD-CAA methods for linear noise prediction by Bastien Caruel, and then LAGOON further analysis of aerodynamics experiment and early acoustics, aeroacoustics results by Eric Manoa. And I think that's the two papers that you need to check if you want to have more details about the case, okay, and the data. And then if you want to compare, they published also a summary before we actually participated to this this workshop, because we published our results for this case on the 22nd AIAA CEAS Aeroacoustics conference last year in 2016, and this summary here was done before that. They are considering publishing another summary maybe next year, so we'll see that. But at the moment, if you want to compare the other code's results and align XFlow on it, check, let's say, the relative accuracy between other codes, please feel free to check on this reference here. I think it really shows that Lattice-Boltzmann has very good, very good accuracy on this kind of problems, but also lower computational costs, which is also very important. And so now we can go through a very brief XFlow acoustics post-processing. I'll do very quickly, just to show you the capabilities we have. So for this, I'll jump to my XFlow session opened here. So I won't detail all the simulation setup here, but well, for those that don't know XFlow yet, this is the XFlow interface, and usually you've got different windows, a project tree on the left, a graphic view where you can actually watch your geometry and see your results as well. You can measure static pressure or whatever from your simulation in the function viewer, and then you've got a timeline. So in that case, looking at the setup, we've got basically a simulation done in a generic rectangular domain. So you can see that the only options that you have to set up in the engine side is that simulation is single phase because we work with only air, external because we want to define the domain with a generic rectangular domain, a box, external box, isothermal, and then we just have to enable acoustics analysis with this button. When it's enabled, the only thing that happens is XFlow is going to match your time step so that the speed of sound is a correct one, and then you'll get the correct, let's say, fluctuations at the correct speed of sound. So that's all, as simple as that. It's not a lot of mystery. You don't have a lot of parameters to set up. Very simple to get ready and work with acoustic simulation. So my domain is set up here. We've got the inlet velocity with plus x here, boundary here, flow goes to minus x. That was specified in the LAGOON case, so we just kept the same things. And here the LAGOON is in a free air condition. That means we didn't put any ground. It was up to participants. Both were perfectly, I think, okay. So we've been going with a free air condition in that case. And then we just set the material properties as defined in the case, which will be what will set our speed of sound for air here. Geometries, very simple. We've got the two wheels, we've got the axle, and then the leg, and the profile here. Finally, just setting up a few simulation parameters, the simulation time, 0.34, the far field resolution of 0.512 meter for the far field. And then on the geometries, you see we've got the list of geometries, just set 0.5 meters on each of them, so that XFlow automatically generates lattice on them. And then the different refinement region that I was mentioning, actually there are some others more than I was mentioning that are larger, so that we can keep a good wake refinement also, generally speaking. But that's basically the ones I showed you in the step of the case, and you can set up the different resolutions for each of them. Okay. Important maybe then to import the different probes, which is very convenient in XFlow. We used a probe file. All probes were, let's say, in a text file that we can import, and then you can see there are all these probes here where we actually measured the acoustics of pressure in these probes here, basically. Okay, and then it's good to go. So very simple things. So what you can do with XFlow then is get access to a lot of numerical data. So you see all my probes that participated in the simulation are available here. I can get access to my static pressure at very high frequency. That's why I use probes instead of sensors. And then you can see, for example, I've got my history of probe pressure against time. So you see a short transient period. So let's say we take from 0.05. In that case, I can just simply use that to do some signal processing. So we've got capability to switch to frequency space. So you see when you go to data management, you can switch to frequency space, also check the SPL, the sound pressure level, or the pressure spectral density as well. So if I try to switch to space of frequency, I can apply this transformation of space using some different window types so that the transition is smoother between in the signal processing, and then I can also use, let's say, a range of time. For example, I want to remove everything before 0.05, so I'll just put 0.05 and leave until the end. I'll accept, and what I'll get is a very large spectra, so what I'll do is I'll try to zoom in very closely, you see, to these low frequencies, because since we've got a very high data sampling, of course we'll get a lot of frequency range in that spectra. And so you can see here we got, for example, here's the resonance peaks that I was mentioning previously in my presentation at 1000 Hertz. Shows here another one at 1400 and so on. So you can see the spectra, for example, in frequency space, or simply check on a let's say the sound pressure level if in your domain. So again, doing a large zoom on the region, you can see the sound pressure level in that region in between 0 and 10,000 Hertz, for example, the same way. So we see again these peaks occurring as well here and here as well. So apart from that, we've got a couple of different options that allows you, for example, to apply filter to signal. So you could just filter the signal before processing it. If I want, I can have a low pass, band stop, high pass filter. I could say I want to check my signal between 800 and 1200 Hertz, for example, which is in between the resonance frequency. Could determine the given window types. I'll get Han, and for example, then adjust my order. So if I want a higher order filter, I can just increase the order. You'll see, then you see better what happens in the magnitude, or also the phase shift induced by the filter. So it's very convenient. You can preview where the filter is applied and the phase shift as well, and then apply your filter to get your signal as well. So basically, it's a simple but complete post-processing. Also, something I didn't mention, we didn't use for that application, but would be very useful, is also the static pressure filters in, let's say, the pressure field. You could also use these filters, but not only in the probe, but also in space. You could use also different types of filters as well, which would be very interesting and would be interesting for the future as well. So I think I'm pretty much done. I think we've got 5 minutes. I'll let now Zaki again the hand for the rest of the sorry, for the rest of the presentation. So Zaki, you've got the hand now.
Okay, thank you, Rudy, for this nice presentation. I hope all the audience has enjoyed this webinar. We have received some questions, so some of them I have already answered some of them, but I have kept some few of them for the end. So the first question: can XFlow perform acoustics analysis in water?
Okay, so yeah, I've been speaking about air, for example, but as you've seen, it's very easy for XFlow to adjust the speed of sound. The only difference between air and water is actually compressibility and speed of sound of your liquid, of your fluid. And so typically with air you've got 340 meters seconds, and for water you would have 1400 meters seconds. So the equation that relates the lattice spacing with speed of sound is is the same, and we just have to change the speed of sound to get another time step.
Yeah, thank you for this answer. We have another question from an attendee asking about the reflection from the boundaries. How XFlow deal with the reflection from the boundaries?
Yeah, that's a very good question. So we indeed, in this case, I didn't speak about this because in that case we're in an external configuration. So you don't have much problems about reflection of boundaries because the domain is large and resolution gets coarser and coarser, so you diffuse everything when you get far enough. So there's no problem about that. But we have in XFlow, let's say, some absorbing and non-reflective boundary conditions called LODI. And actually in this paper where we published the LAGOON results for the AIAA Aeroacoustics conference last year, we also published a case on the orifice duct where we actually use and show the utility of such boundaries. So in that case we have also this possibility. We just didn't use it in the LAGOON case just because it was not very relevant.
Okay, thank you very much, Rudy. I think we will stop here. We have already exceeded time. So thank you very much, everyone, for joining this webinar. Sorry for the questions that we could not answer. We will try to answer them by email. If you have more questions, you can send your questions to me by email after this webinar, and we will be happy to answer them. We will make this webinar has been recorded, so we'll make the recording of the webinar available soon. Thank you very much. Thank you, Rudy, for your presentation, and see you next time. Bye.
Thank you, everyone. Bye.